In this video, we're going to find the solution to constant coefficient homogeneous linear ordinary differential equations. The idea is to use an auxiliary equation, solve that, and then see what that tells us about what the solution should be. So I'm just going to start with the first few of them. If we have y prime plus 2y equals 0, notice that these are constant coefficients. The coefficient there is 1, and the coefficient there is 2. It's homogeneous because it's set equal to 0. And it's linear because it takes the linear form, and it's a differential equation because of the y prime. Okay, the auxiliary equation, by the way, this happens to be first order because there's only one derivative. The auxiliary equation is given by m plus 2 equals 0. Solving that, we get m equals -2. So our solution, which we're going to call y sub h, h for homogeneous, is any constant times e to the -2 x. It's as easy as that. Solve your equation, it's e to the mx, more or less. Let's see. What if we had something a little trickier? In this case, this is number 6. We have y double prime plus 2y prime minus 3y equals 0. Well, it's the same procedure. We go to the auxiliary equation, which is m squared plus 2m minus 3 equals 0. Make sure, by the way, when you're writing this out for me, for instance on a test, that you write it out as an equation. That is to say, you set it equal to 0. In this case, I think this one factors. As m minus 1 times m plus 3. And so my solutions are -3 and 1 for the auxiliary equation. Since these are distinct real numbers, our homogeneous solution looks like C1 e to the -3x plus C2 e to the x. Okay, well, let's try another one. I'm going to erase our first order problem. Imagine we have something like number 10, which is y double prime plus 6y prime plus 8y equals 0. Again, we write out our auxiliary equation. In this case, it's m squared plus 6m plus 8 equals 0. And this one, once again, factors. And we get roots m equals -4 and -2. Since these are, once again, distinct real numbers, the homogeneous solution, y sub h, is C1 e to the -4x plus C2 e to the -2x. Is it the case that they're always going to factor nicely? Probably not. But let's see if I can pick one out that doesn't. How about number 19, just picking one at random? Y double prime minus 6y prime plus 17y equals 0. The auxiliary equation is m squared minus 6m plus 17 equals 0. And I can see pretty quickly that this is not going to factor at least nicely because 17 is prime and only has factors of 1 and 17. And no combination of that is going to give me -6. So from here I can just go ahead and do the quadratic formula if I want. This tells me that m is, how does it go? -b plus or minus the square root of b squared minus 4 times a times c all over 2a. Well, that's not terribly pretty, but nothing for it. Four times 17, we can do a quick calculation here, is 68. So we get 36 minus 68. Subtracting 36 from 68 yields 32. So we get 6 plus or minus the square root of negative 32 over 2. Oh man, it seems like this problem never ends. We need to simplify this. I can pull out a perfect square from 32. 32 is 16 times 2. So it's 4 times the square root of negative 2 over 2, which is 3 plus or minus 2 root 2 I being the square root of negative 1. Now, we have complex roots in this case, and that changes the form of our answer. The complex roots solution depends only on alpha and beta, the real and imaginary parts of our complex number. So what we're going to do is use our pattern for the exponential, which actually goes through Euler's formula. It's c1 e to the alpha x, so e to the 3x, cosine beta x, so cosine 2 root 2 x, plus c2, and then e to the alpha x, so e to the 3x, sine square root of 2 times 2x. And that's it. So this is what we do for complex roots. We pick out the alpha and we pick out the beta, and then we say, oh, okay, well, it's e to the alpha x cosine beta x and e to the alpha x sine beta x. Overall, not terrible. We just have to remember to do it and not be afraid of complex numbers. Now let's try another one. So I'm just skipping around and trying some random ones. How about y double prime? I wrote 14 here, so y double prime plus 4y prime plus 4y equals 0. Okay, well, what do we do? By now, hopefully it's familiar. We write out the auxiliary equation. In this case, it's m squared plus 4m plus 4 equals 0. This one actually is a perfect square. It factors as m plus 2 quantity squared equal to 0, which means I only have one root now. Well, luckily, we have a repeated root case for the solution of our homogeneous equation. So we can just go ahead and write down what we should get. c1 e to the negative 2x plus c2 x e to the negative 2x. And that's it. So what we've seen are examples of how to find the homogeneous solution of a constant coefficient linear ordinary differential equation in a few different cases. We've seen what happens when you have distinct real roots. Those are our first couple of examples. We've seen what happens when you have complex roots, like this one. And we've seen what happens when we have a repeated real root.